Training 100 billion parameter foundation models requires massive physical infrastructure. Pushing trillions of tokens through a deep neural network demands multi-node supercomputing clusters operating at peak capacity, generating immense thermal output and exorbitant energy costs. This visualization compares the capital expenditure required to customize these models. Full fine-tuning a 7 billion parameter model requires over 100 gigabytes of VRAM, roughly $50,000 in enterprise graphics processing units. For a developer, a consumer-grade GPU costs $1,500. This chart shows how dense optimizers cripple VRAM capacity. Base weights are a fraction of the bottleneck. Tracking gradients, momentum, and variance for every parameter during backpropagation exhausts VRAM. Scaling this across a 100 billion parameter model creates a hard memory wall. Updating the entire network architecture for every new task is mathematically intractable. Without an algorithmic intervention, aligning generalized foundation models to specific domain tasks remains economically restricted to a fraction of the industry. The core dilemma of transfer learning is structural. Engineers need to inject precise, specialized behavioral traits, like medical coding or legal summarization, without overriding the pre-trained syntactic knowledge derived from trillions of tokens. Massive neural networks possess intrinsic dimensionality. While containing billions of parameters, their learning capacity is highly compressed. Task-specific adaptation naturally exists in a low-rank subspace. Necessary weight updates are structurally dense, but mathematically rank deficient, meaning only a tiny fraction of parameters must change. This mathematical reality changes the engineering protocol. Rather than scaling hardware arrays to brute force a full parameter update, developers can freeze the pre-trained weights and target that low-rank subspace directly through geometry-aware optimization. Parameter-efficient fine-tuning, or PEFT, provides an elegant mathematical correction to an inefficient training pipeline without compromising model intelligence. It allows the model to specialize while keeping its foundational knowledge intact. This flowchart details 2019-era additive adapters. Engineers inserted small bottleneck networks directly between the layers of the standard transformer block. Because this architecture is sequential, the activation tensor pauses at every layer, creating a compounding latency penalty that slows down production inference. In 2021, LoRA offered an algebraic solution, representing the weight update as two distinct low-rank matrices. The input vector multiplies against the frozen base matrix and the trainable pathway simultaneously, reducing parameters by 10,000 times. Post-training, these matrices seamlessly merge into the base weights. This merging process eliminates the inference latency penalty. The resulting model carries its new task context within a unified architecture, creating a scalable, zero-overhead method for model adaptation. In a traditional serving environment, hosting 10 custom models for 10 different clients requires loading 10 independent 40-gigabyte weight matrices into VRAM, instantly exhausting hardware capacity. This VRAM map illustrates a dynamic multi-adapter architecture. A monolithic foundation model resides in memory permanently, sharing the GPU with hundreds of megabyte-sized adapter stores. When diverse requests arrive, specialized kernels broadcast the base weights while mapping individual requests directly to their specific adapters. However, routing through unmerged adapters creates a new problem. Switching between different adapters mid-conversation forces the system to flush the key value cache, causing noticeable latency spikes for the user. Advanced frameworks mitigate this using activated LoRA, or ALora. By utilizing base-aligned block hashing, ALora permits cross-model cache reuse, preserving the shared foundational activations even as the active adapter swaps. This allows a single deployment endpoint to behave as a swarm of highly specialized models, maximizing hardware utility and the return on AI investment. Standard low-rank matrices occasionally fail to accurately mimic the proportional learning dynamics observed during full fine-tuning. This creates a performance gap on complex tasks where simple matrices lack the necessary expressivity. To close this gap, weight-decomposed low-rank adaptation, or DoRA, manipulates the geometric properties of the weights directly. DoRA pulls the pre-trained weights apart into two distinct variables, a scalar magnitude slider and a separate multi-dimensional directional compass. Instead of updating both, DoRA locks the low-rank update into the directional compass. The magnitude vector adjusts independently, mirroring updates seen in full-scale training. Correcting the geometric dynamics of optimization allows low-rank methods to rival the deep reasoning capabilities of full fine-tuning without adding any additional parameters. Until recently, parameter-efficient training required limiting the model's physical search space to rigid structural bottlenecks, essentially capping the number of weights that could physically change. Gradient low-rank projection, or GaLore, removes the requirement for structural bottlenecks. It demonstrates that engineers can maintain full parameter expressivity, where every network weight can potentially update, by compressing the optimization statistics rather than the weights themselves. During GaLore's algorithmic execution, the backpropagation step calculates the full dimensional gradient, immediately projecting it into a compact subspace using singular value decomposition. The optimizer tracks momentum and variance strictly within this tiny subspace, reducing memory by over 65%, before expanding back to update the full-size weights. By moving this low-rank constraint into the gradient calculation, GaLore enables full-scale model updates using only consumer-grade hardware. Parameter efficiency has mathematical limits. Because low-rank matrices intentionally restrict information bandwidth, they are structurally suboptimal for injecting vast amounts of novel factual data, like deep biomedical literature. This matrix shows for factual data retrieval, RAG is the superior architecture, grounding responses in external documentation without altering model weights. Conversely, teaching a novel logic framework from scratch strictly requires full parameter updates, despite the immense compute cost. The operational sweet spot for PEFT is behavioral alignment. It excels at permanently ingraining precise stylistic constraints, JSON formatting, or domain-specific tone directly into the latent space. Treating parameter efficiency as a panacea for knowledge injection leads to a specific failure mode, a model that generates fabricated facts, perfectly formatted in the exact style you requested. The portable nature of adapters has birthed decentralized repositories where developers freely share PEFT modules. This creates a porous, open supply chain where untrusted modules can be integrated directly into live production systems. Maliciously crafted adapters can behave normally during testing, but trigger a payload when presented with a hidden cryptographic string. These backdoors can force the model to extract sensitive data or bypass safety guardrails. The system is also vulnerable to combinatorial attacks. Loading two entirely benign adapters simultaneously can cause mathematically unforeseen interactions that break the model's alignment, even without an adversarial user. The primary innovation of PEFT is the explicit structural decoupling of general knowledge from task-specific behavioral alignment. By mathematically isolating the parameters strictly required for task adaptation, PEFT neutralized the hardware bottleneck. Foundation models have moved beyond high-compute research environments to become modular, globally deployable engineering tools.